ジョーはヘロクの中でいろんなJava 言語によってなんか彼は Java 言語のオーナーでもしヘロクはビルパックの関係で色の関係でJava のことによって彼はその全部のオーナーになっています。Java っていう言語は多分知らないけどもし知らない人 Java は JavaScript と一緒同じ。はい。ではジョー・カットナー拍手をお願いします。
Hello, can you hear me? Yeah. All right, well, welcome to Asynchronous and Non-Blocking I.O. with JRuby. My name is Joe Kutner. I go by Codefinger online and IRC, Twitter, all the internet places, and I work at Heroku. I've also written a few books. I wrote a book called The Healthy Programmer, which has been translated into 5 different languages, including Japanese. And I wrote 2 books on JRuby. Which is why most people consider me the world's leading expert on Tom and Charlie's beer preferences. So if you need to get them a gift, I'm the person to ask because I have great ideas. But yeah, we're going to talk about JRuby today, and we're going to talk about using it in a unique way. Before we talk about that, we need to talk about how most people use JRuby or Ruby. So most Ruby applications using Rails or Sinatra, the typical web frameworks, handle requests with a single thread per request. And that thread blocks the entire time it's servicing that request. So if it has to go do some database work or hit some external service, that request thread is going to block and wait the entire time that service is doing its work, even though that thread that's handling the request isn't actually doing any work. And we call this blocking wait, and it's a waste of money. It's kind of bad. Because each of these threads consumes resources. And the only way that we can scale a system of this nature is by adding more threads. So when we add more threads, we're consuming more memory because each thread has its own stack frames. We're putting more strain on the CPU because it has to do more context switching. Also on the CPU because the GC now has to walk more stack frames. So at the end of the day, we're consuming more resources and we're spending more money. So what we want to do, and what we're going to talk about in this talk, is asynchronous wait. So handling a request and doing some kind of I.O., either hitting a database or some external service, and then releasing the thread that's handling that request so that it can go and do other work. So in this way, we can use a single thread to handle multiple requests at the same time. We can also do asynchronous or parallel access of I.O., so we can hit a database or some other external service in parallel while our request thread is unblocked. So in this new asynchronous and non-blocking model, we're saving money. Each request uses fewer resources. Multiple requests can share a single thread, which means that we need fewer threads, which means that we need fewer money, or fewer servers, which means that we're going to spend less money. So this may seem like a technical talk, but this is really like a financial talk about using your resources better, being more efficient, and ultimately not spending so much on servers. And of course, this is what a lot of major companies are doing, Apple, Google, Twitter. I mentioned these ones in particular because they're all using a specific piece of technology, which I'm going to talk about today, and that's called Netty. Netty is a Java framework. It's a framework, a library for doing high-performance, non-blocking, and asynchronous I/O, or asynchronous TCP, both servers and clients. At Apple, Apple is probably the biggest user and contributor to Netty. They're running 400,000 instances of Netty in production. They're handling tens of millions of requests per second and tens of petabytes of data per day. This is from 2015, so I'll assume nothing has changed because it's Apple. But they call this massive scale, and the reason they're using Netty in that way is because it's a very low-level library. Okay, so you can think of it kind of analogous to Rack. It's this low-level thing that if they have very specific use cases, they need to go down to Netty. But what we're going to talk about today is going up a level, and we're going to use a framework called Ratpack, which is a high-performance micro framework, kind of analogous to Sinatra, for building web applications on Netty. So Ratpack sits on top of Netty sort of in the same way that Sinatra sits on top of Rack. It provides a very lightweight environment that's conducive to building web applications. The difference from Sinatra, though, is that Sinatra, even if you're using it on JRuby and on the JVM, is that you can handle requests in parallel, but each of those requests belongs to a particular thread that's blocking and blocking the entire time it's processing that request. Ratpack uses an event loop, the event loop that's provided by Netty, so that each request, for the work that it has to do, the I/O, those kinds of interactions, it creates an event that is put on the event loop that's processed asynchronously, releasing the request thread so that it can go and handle other requests. So at a more fine-grained level, this event loop concept has event emitters, which are generating events which get queued up into the event loop, which processes them in serial. Each event generates a result, and then that result is passed to a handler. And then that handler may continue the cycle. It may also be an event emitter. So in code, this construct is the promise. So if you've used Node.js or maybe concurrent Ruby and you're familiar with a promise, this is the same concept. There are many ways to create promises in Ratpack. Virtually everything that you do creates a promise, actually. But one of the most common methods is to take some code that's going to do I/O, like some database interaction, and wrapping it with this blocking.get method. So when we call blocking.get, we pass it a closure, or a block. I just don't want to say block too many times. And the closure will contain some code, like an active record interaction, something that's going to do some I/O. But that chunk of code will not be executed immediately. It'll be stored off for later execution. And the get method will return to us a promise. And that promise represents a unit of work, an execution segment, that it promises to complete at a later time. It's not until we call promise.then that the execution segment is queued up to be executed, to be run on the event loop. So the then method, we also pass it an execution segment, which is the execution segment we're going to run against the result from our original execution segment. So looking at this with the event loop, we have an execution segment when we call blocking.get. It's put on the event loop, which generates a result, which is passed to the next execution segment, and then the cycle kind of continues until we've finished handling the request. Okay, so I've got an example application. It's very synthetic. It's just designed to demonstrate how Ratpack works, and we're going to walk through how it's built and how it works. So the simple application takes a request from a client, a browser, with some search terms, and then for each of those search terms, it makes a request to the eBay API to see what items are for sale that match that search term. So if we give it 3 search terms, it's going to make 3 requests to the eBay API. It has a landing page, and it makes these requests in a bunch of different ways. So the landing page shows different ways of making those API requests, both in a blocking fashion and a non-blocking fashion and a parallel fashion, and records how much time was spent blocking the request thread. So where it's red, the request is blocked, and where it's green, it's not. So I'll go over this in detail in a moment, but the key point here is that it's doing this in various different ways. So let's take a look at the example that blocks when it makes a request to the eBay API. So we'll talk about how the application is built, how it's structured later. I just want to dive into the code that makes these requests. So this is the code that you would have in your request handler, so like your Sinatra get method. It's just isolated here. So in this example, we have some search terms. We're going to iterate over each of those terms. We're going to generate a URL for that term. So that's the URL to our eBay service. We're going to use net http.get to make a get request to the eBay API. And then it's going to return a response in JSON, which we'll parse. And then we put all of those into a list, and then we render them to the client. So each time we go over these search terms, and we call http.get, we're blocking. Our thread is waiting until eBay returns something to us before we go on to the next one. So it looks kind of like this in a sequence diagram. We have our client requests, we make multiple eBay requests, and our request thread is blocking the whole time, so it's blocking wait. The asynchronous example looks fairly similar. We have a list of search terms that we iterate over. We create a REST URL for them. But in this case, instead of using net HTTP client, we're going to use the HTTP client that's provided by Ratpack. So Ratpack has an HTTP client that uses the Netty event loop to process HTTP requests. So when we call, in this example, HTTP client.get, we're not hitting the wire. We're creating a promise. So this get call, instead of hitting the wire, creates a promise, and a promise that it's going to make an HTTP request. It's when we call .then that it actually queues up that event on the event loop. And then it has a callback handler which processes the result. And finally, we have another promise that for rendering the result, so doing that on the event loop as well. So in this example, what we've done is we've taken the same pattern as before, and just during those periods where we're waiting for the eBay API, our request thread is now free to go do other work. But there's a problem with this. It's still serial, right? So even though our request thread has now been freed up to go do other work, it's still going to take the same amount of time to make each of those eBay requests. Now, this may be what you want if each of those eBay requests depends on the previous request. So the formulating the URL depends on some output from the previous call, then that may be what you want. But in our case, we don't care. We can do all of these in parallel. So the third handler in this example, I'm sorry. So the reason this happens is that the event loop in Netty is single-threaded. So as these events are queued up, as we're calling http.get, we're creating new events that get put onto the event loop and then are processed on a single thread in parallel. Fortunately, the Netty event loop is actually multiple event loops. There's a pool of them, and they each have their own thread. And Ratpack provides mechanisms through which we can tell the system to put these events onto different event loops so that they can be processed in parallel. And that example looks like this. The first thing you'll notice is that it's quite a bit more code. Well, a little bit more code. And it is, I think that's important because it's not, this asynchronous and non-blocking method is not free. There is a cognitive overhead and a code overhead to doing this, but we gain a lot of power, right? So that said, we're going to start by iterating over our search terms. We get our Ratpack HTTP client, and then we call HTTP client.get. So we get our promise, but we're not going to call then yet. We're just going to collect those promises of making those HTTP requests, and we're going to put them into what's called a parallel batch. So parallel batch comes from Ratpack. It's a convenience class that takes a bunch of promises and batches them into a single object that we can apply functions to. Then we have to create a thread-safe array. So synchronized list is a method from the Java standard library that lets us create a thread-safe array because we're going to now operate on that array from multiple threads and multiple event loops. Then for the batch, we iterate over each of our promises, and we add to it a handler. So this is the same handler we had before. We're going to get the JSON response. We're going to parse it. And that's going to return to us an operation, which is actually just another promise. We call it operation, but it is a promise. And then finally, we call operation.then, and we render our results. So when we call operation.then, all of the work that has been promised for us to do is actually going to be queued up on the event loops and then finally executed. But it will be executed not on the request thread, not on the thread where we've set all of this up. So what we've done is we've taken our non-blocking model and we've compressed it into a parallel model where all these operations are happening at the same time. So on that landing page now, we have the top row, 2 columns, where it's making that blocking request. It's using net HTTP to make an HTTP request, and the request thread is blocked the entire time. That's why it's red. So on the left, we have a single search term, and on the right, we have 3 search terms. And so 3 search terms takes about 3 times as long. The middle 2 are where we're doing the asynchronous request, but we're doing them serially. So on the left, it's 1 search, so it takes the same amount of time, but it's green because that request thread has been unblocked. And then on the right, we're making 3 requests. The request thread is freed up to go do other work, but it still takes about the same amount of time because we're waiting for each one to finish before we go on to the next one. And then finally, we have the asynchronous and parallel example. And you can see it takes a little less than half the time to make those 3 requests. and there's just a sliver of this that the request thread is actually blocking. So you can just see barely there a little bit of red on that bar. Okay, so let's talk about how this application is built, how it's put together. If you were to go look at this on GitHub, you would see a Ruby application that looked very familiar. There's a gem file, there's a rake file, there's a lib directory with some RB files. There's no XML, there's no .java files, there's none of that weird stuff. This feels very much like a Ruby application. So in the gem file, we define JRuby as our engine, and we could put any of our gem dependencies here if we're using Nokogiri or Active Record. This is a very contrived example, so we only have one dependency, which is JBundler. JBundler is a JRuby library for having dependencies on Java frameworks and Java libraries as if they were Ruby gems. JBundler has its own descriptor, a jar file, capital J-A-R file. And just like we define our gems in our gem file, we define our jars in our jar file. So we have two jar dependencies, the Ratpack core library, and then SLF for JSimple, which is just a simple logging library that Ratpack uses to log to standard out. So then when we run bundle install, Bundler will install JBundler, and from then on we can run JBundle install, which will actually handle running Bundler itself and also installing those jar files that we depend on. So you would see it installs Ratpack core and all of its dependencies, which include Netty. Now this application also has a single .rb file. Again, it's a very contrived example. But this server.rb file is the entry point for the application. It's a Ruby script. The first thing we do is require Java, which is what most JRuby applications do, which gives us access to some convenience methods and other things that JRuby provides for us. Then we set up Bundler as normal, and because we're using JBundler, setting up Bundler is going to set up JBundler, which is going to put those jar files on our class path. And that allows us to use Java import, which comes from the JRuby, I guess, standard library. It allows us to import the Ratpack server class, which is a Java class, but by Java importing it, we can now use it as if it were a Ruby class. So we can run ratpack server.start. This is how we start our Ratpack server application, and we pass it a block, and that block contains our entire application. So most real applications will sort of decompose what's in here into other classes, but in this case, the entire application is contained in this one file. So in this block, we define our handlers. Those are, it's a construct in Ratpack for how we process requests. We have a handler chain, and each handler matches a certain request route, and we can potentially match or apply multiple handlers to a single request route. But in this case, we're just going to have a handler for the async path, so invoking localhost or opening a browser to localhost/async. This handler will be applied. And then in the block that's passed to that, we put all that request handling code. So you would literally copy the code that we saw earlier for doing the asynchronous request and paste it in here. That's your entire handler. And then we also have one for a GET request to the sync route. And again, copy that net HTTP code and paste it in here, and that's your synchronous GET handler. All right, and then with that server RB file, we run it just like any other Ruby script. And it will bind to a port and start up our Ratpack server, and you can access it on localhost. So this example is on GitHub. That's the URL. It's ready to run locally. It's ready to run on Heroku. It has a Heroku button so you can deploy it very quickly. But it's a very contrived example. Just demonstrates some basic functionality about using Ratpack. Now we'll move on to a more real-world-like example called the books example. This is actually an example that comes from the sort of official Ratpack repository. It's an example application that they maintain in a couple different languages, and I've ported it to JRuby. It is an application that simulates a bookstore or library management software. So it has an inventory of books and their prices and all the information associated with those books, and then you can manipulate it to just perform CRUD operations on it. So to have this information, it comes from two data sources. A local database, which maintains inventory and pricing, That's what our library or bookstore has. But then all of the generic information about the books comes from a service called isbndb.com. So this provides the ISBN number, which is like a unique identifier for a book, provides the author, the title, the publisher, the publishing date. All of that generic information that's the same outside of our organization comes from there. And the job of our application is to take these two data sources and merge them into a single domain object that we use inside of the application to represent a book. So it's a bit more complex than just making asynchronous parallel requests to the eBay API. So to do this, we're going to need some more powerful tools. We're going to use a library called RxJava, which is used to compose and transform asynchronous operations. It's maintained by a group called ReactiveX. Rx stands for reactive. They maintain a number of different libraries like Reactive Java, Reactive JavaScript. There's an RxRuby, but we're going to use RxJava because it has excellent bindings to Ratpack. So Ratpack offers first-class support for RxJava. We're going to combine that with a library called Hysterics, which comes from the OSS group at Netflix. Hysterics is a library for wrapping I/O operations and applying fault tolerance, caching, deduping. So if we have a number of events queued up on our event loop, it can determine if some of them are the same and then not perform the same request twice. But we're really going to focus on RxJava, which uses this construct called an observable. An observable is very similar, sort of analogous to a promise, and that is, it's a unit of work that is going to be done in the future. It may be done asynchronously, it may be done synchronously. That's sort of irrelevant. The idea is that it's an object that we can reason about, that we can apply transformations to, and that we can compose with other objects. For example, we can take multiple observables and apply functions to them to turn them into other observables or to generate other kinds of results. We can apply a timeout to an observable. So from another thread, we can have a handle to that observable and tell it, if it hasn't completed by such and such time, just kill it. We can zip multiple observables into a single result. This is how we're going to, how the application takes those multiple data sources like the database and the ISBN-DB service and combine them into a single book object. So to add RxJava and Hysterics to our application, we edit our jar file and we add Ratpack Rx, which is the Ratpack bindings for RxJava, and then Ratpack Hysterics, the first-class support that Ratpack has for the Hysterics library. This sample application, also has a server RB, which is again the main entry point to the application. It has a number of other classes as well. The beginning of the class looks identical, pretty much identical to the synthetic application, or the synthetic example. Sets up JRuby, sets up bundler, has a few Java imports. Then we call Ratpack server.start. In this case, we're creating a book service as the first thing we're doing when our server starts up. The book service encapsulates all of the operations that we need to interact with our book inventory, both the local database and the ISBN-DB service. Then we start our handler chain, and we have, in this example, we have handlers for getting all of the books, getting information about a single book, editing a book, adding new books, deleting books. But we'll just look at the handler for the default route, so just like localhost / which gets all of the books and shows the complete inventory for our bookstore or library. To get all of the books, we call bookservice.all, which is going to return an observable, and then we're going to subscribe to it. So this all method, sort of like our HTTP GET return to promise, this all method is going to return an observable, which we then subscribe to, and the subscription, much like the .then method, we pass it a handler, so it's going to handle the result from that observable, and then just calls a method to render the ERB for the web page. So let's take a look at the book service class. When it's instantiated, it sets up two command objects that handle the interactions with the local database and with the ISBN service. And then it has an all method, which is what we saw invoked earlier. So the first thing it's going to do is call db.all, which is going to get all the books in our inventory. That's going to return an observable, and then it's going to map that with the result from the ISBN DB service. We're going to get an individual book for each result in our local database. And then we're going to merge those together and return it. So again, we have the all, which returns an observable. That observable from all is not a list of results. It is an observable that emits multiple values. So we need to map that is, map each result that's emitted by that observable by applying a function to those values. So that value is a row, which is passed into our block here. And then for each row, which has an ISBN number, that's from our local database, we call getBook, which also returns an observable. So an observable that emits a single book. We're going to map that. So we're going to apply a function to that result. And then we're going to merge it with the row that was returned by the database. And that's going to return an observable that, again, emits results, or emits items. We need to convert that into a list. So what we need is an observable that emits a single Ruby array. And that's why we call toList here at the end. And that ultimately is an observable. So that's the observable that in the previous code we subscribed to. So again, we have all, which returns an observable that emits items. We're going to map that observable. So we're going to apply a function to each item from that observable, which then in turn returns an observable that emits items. We have to convert that to an observable that emits an array, a single object, and then finally subscribe to that. But more generally, what's happening here is we have multiple observables, and we're applying operations or transformations to them. And we just keep chaining through this until we've transformed our observable into what we want, and then we finally subscribe to it. This is how RxJava works. Okay, so now let's take a look at the bookDB command. So this is the class that our book service had an instance of for interacting with the local database. This class makes database requests, but it wraps those database requests with hysterics, which is the Netflix library. So this is a lot of what the code you see here is actually boilerplate. This is one case in using Ratpack and all of these libraries where the JRuby abstraction on top of these Java frameworks does bleed through. So you can see, like, we're creating what's called an anonymous class in Java. It's like a class that doesn't really have like a name, and that's just due to the way that the hysterics library works. So I think there's potential here to create a like JRuby hysterics gem that hides all of this, but nobody's done that. I haven't done that. So there's a little bit of boilerplate here. But the key thing that's happening here is that we have a database. So I'm using SQL here. So it's just DB, and then it's a SQL statement. And it's going to get all of the books in our inventory. And then it wraps that in blocking.get, just as we saw earlier. So blocking.get returns a promise. So Ratpack's first-class support for RxJava provides a method observeEach, which takes a Ratpack promise and converts it into a RxJava observable. So this Rx Ratpack observe is going to return that observable that emits items. So that's in our the construct method of a hysterics observable command. So this is a command object from the hysterics model, and hysterics has integration with RxJava. So hysterics knows what an RxJava observable is, and we can construct a hysterics class that returns an observable. We can also do things like give it a cache key. This is what it uses for caching and deduping and things like that. There's also some more of that boilerplate up above where it's like adding a command key and putting them into groups. The hysterics library is very powerful, and it allows us to do lots of different things that I won't go into. But ultimately, it's going to create an observable that represents the unit of work of making that database request, or that database execution. Okay, so this example is on GitHub. Again, ready to run locally just with a simple Ruby command. Has a similar structure to the synthetic example, also ready to run on Heroku. Now, I focused exclusively on Netty in this talk, and Netty via Ratpack. But there are several other ways to do asynchronous and non-blocking I/O with JRuby and even with MRI Ruby. We could use Warbler and the Servlet 3.1 async spec. So this is a very stuffy way to do async in Ruby. But Servlet is a Java specification for doing asynchronous I/O with Java servlets. We can also use Vertex, which is an open source web framework that has its own implementation of the reactor pattern, has its own event loop that it uses to do asynchronous and non-blocking I/O. It works with many languages, including Java, JRuby, Clojure, Kotlin, but uses ultimately some different internals. And then, of course, we can use Event Machine, which works both with JRuby and with MRI Ruby. But with Event Machine and with some of these other ones, like Servlet 3.1 async, the challenge is that it becomes difficult to avoid callback hell. So callback hell is this concept for having a bunch of asynchronous operations and not or events and not being able to reason about what is happening in what order. And you become lost in this sort of mess of callbacks that you can't follow in your mind very well. That's callback hell. It can happen in Ratpack, but what Ratpack provides for us is some guarantees about order of execution. So as we saw with the eBay example, where those requests were happening serially, and we had to go out of our way to make them happen in parallel, that's a guarantee that's provided by Ratpack that if we create promises in a particular order, that they will be enqueued in that order and ultimately processed in that order. And that helps us reason about the code that we're writing. Event Machine is also not integrated into your web framework the way that Ratpack is. You know, it has its own HTTP clients, those kinds of things. But if you go to the Event Machine documentation, you'll see it actually describes itself as being much like JBoss Netty. They are both implementations of the reactor pattern. That's where we get this event loop from. So those are all of the virtues of doing asynchronous and non-blocking programming, but there are some maybe drawbacks or some potential cases where it's not a good fit. If your bottleneck is a database, so that your application scales at the rate that your database scales, so all of the work, all of the heavy lifting is done by the database, then making asynchronous calls to the database such that you can handle more requests is only going to put more load on your database. So it's not going to provide any improvement in your applications. If that's the case, then this pattern, this cognitive overhead may not be right for you. And as I was saying, cognitive overhead, asynchronous is hard. We saw that with the asynchronous parallel example that it does involve more code. It is, asynchronous programming can be non-deterministic. For example, we had to create that thread-safe array in the asynchronous parallel example. Those are the kinds of things that you have to account for when you're doing this model of programming. We can potentially have callback hell, and then error handling and propagation becomes more difficult in this environment. So if you get an error in an asynchronous observable or promise, you have to propagate that error back through all of the transformations or all of the other observables that you've been executing, and that can be challenging. But that said, I think there are great benefits to asynchronous and non-blocking I/O, and I spelled async wrong. You stand to gain a lot from this, and I think what's really great about doing it in the way that I've described with Ratpack and with Netty is that it still feels like Ruby. It is still Ruby code, and it's still pleasant to work with. So here are some links. For more about JRuby, there's jruby.org, Ratpack at ratpack.io, Netty at netty.io. The ReactiveX group has a website for all of the libraries that they maintain, RxJava, RxRuby, and then documentation for all of the various transformations that can be applied to observables. And then my two examples that I discussed are on GitHub. So thank you for joining me today. I guess thank you to Heroku for allowing me to be here. And I'll open up to any questions.
Hey, I was curious, it sounds like you work with this a fair bit. I haven't done much with the JRuby observable and reactive stuff. But working in like a framework like Twisted or Akka or something like that, I find it's really easy to let like a promise drop on the floor, for example, and never resolve, and then it's really hard to find those kind of things. Have you had to dig into that? And if so, were there any kind of tools that popped out in this ecosystem for finding things that never resolve, or finding actors that error out, that kind of thing?
Yeah, I know what you're referring to with regard to Akka. No, I mean the short answer is no. I don't have any good answers, or I don't have any good suggestions. But I think that's a really good example of one of the drawbacks that I was describing. Right, is like a closure that you pass to a synchronous method, you don't have any concern about whether that's going to be executed or where the error is going to go. Yeah, that's a challenge. But I do think like having worked with Akka, that like the model that's used in Ratpack, specifically Ratpack and with Netty, and these guarantees that it provides about order of execution do make those problems easier to deal with. So that ultimately, like, I don't have a good answer other than this type of model makes it less likely for that kind of problem to happen.
Thanks.
Well, I've not done a lot of work with using these JRuby frameworks, but I am rather familiar with Event Machine. I've used it a lot, right? And you mentioned about callback held and all of that. Well, I've actually built several contrivances which have several callback layers that are many layers deep. And one of the things that the new Rubies have added that helps with this is are the fibers, right? There was a talk about them yesterday, I believe, right? And, well, have you tried using them over here with on your side, and how
No,
well
no, I
they
haven't.
work? Yeah, well, I've tried to use those with Event Machine. They've really helped a lot in making the code more linear, so to speak, right? So that's one thing.
Cool. Yeah, I don't have any like predisposition about whether you should be like. This is a talk about JRuby. I like JRuby, using JRuby, but I think the bigger takeaway here is that there is this model of doing things that in a more efficient way by unblocking our request threads or whatever, and whatever tool you choose to do that is fine. The example I have here, I think, is novel because it is a Java framework, and it is so like mature and well supported. Like I was saying, Apple, Facebook, Twitter, these are contributors of this project, right? So it's a mature model. It has a lot of the kinks worked out. But yeah, there are definitely other ways to do it.
日本人たちももし質問があったら聞いてください。日本語でもいいから。Please feel free to ask questions in Japanese as well. I will try to translate. それで終わりましょうか。Okay, I don't think we have any more questions, so one more round of applause for Joe, please.